y-axis we have size, and on the x-axis we have intensity. And when we talk about classical optics, so what we usually talk about is lenses, mirrors, right? And these are the elements which are bigger in size. So typically, if you have seen an optical setup, so the lenses are usually there, mirrors are there, beam splitters are there. So they are big elements, big as compared to what we will talk about. So we have lenses, and when we talk about intensity, we usually use higher intensities. So we do not use picowatts, but we work in the range of milliwatts. That is what we when we say we have higher intensities. So that is about the classical optics. As you go towards the nanophotonics, here what happens is that in nanophotonics the size gets reduced and intensity still remains the same. So we talk about milliwatts, but the size is going down. What do I mean by that? So we typically talk about nanoparticles, or we talk about meta surfaces. Suppose we have a substrate and we have small things are prepared using e-beam lithography or reactive ion etching and different methods. So that is mostly nanophotonics. Then what happens if we reduce the intensity? So when we reduce the intensity, but we still uses bigger sizes. So we use the same lenses, objective lens, you might have seen microscopes and all that. So we use the same lenses, but we reduce the intensity. So now we are talking about picowatts, let's say, femtowatts, very small amount of intensity. That's where quantum optics domain comes. And in future, we will also go towards the direction of quantum nanophotonics. So meaning we will be having very small amount of miniature meta surfaces, meta lenses, these kind of devices, and we will also be dealing with very small intensity. So this will come up at some point in future. But typically what we are now dealing is usually lies in the domain of quantum optics. And as you also know, we have discussed about photodiodes. So basically, photodiode is a electronics item, let's say, and what we have is an N-type material and a P-type material, and then there is a depletion region, and we connect this negative with the positive terminal, and we say that we are in the reverse bias, right? Then what happens is that we shine light, and we talk about it that light has two different domains. So you can consider this as a wave, or we can also talk about in terms of photons, but here we will talk in terms of photons. So there is a photon which has some power, which is incident power P in, and this power is nh mu, where n is the average number, right? And then we define some terms like responsivity, noises, and all this about this detector. But that is all about the detector. Now, today, the aim is to discuss about the source. What is happening at the source level? How to describe sources? Because that is what limits the fundamentally limits the quantum detection. So detector is there. There is some limitation from the detector side. For example, the detector dead time. We will discuss about that. That is the limitation from the detector side. But the source itself, the point from where the photons are coming, that itself limits us that we cannot detect beyond a particular threshold. And what is that? That we will discuss. So if you remember, in this direction we have talked about, so what could be, let's say, the problems. So the first problem is noises. So we discuss about thermal noise and all that, right? So thermal noise is one problem. One can cool down the detector, so thermal noise, let's say, is gone. But then we also have heard about the flicker noises or white noise. And then the third point is maybe short noise. So noise is the secondary thing which creates problem while detection, because you always want more signal and less noises. So SNR ratio should be higher. This is always the aim when we use detectors, right? So signal should be higher, noises should be lower. And these are primary type of noises which we discussed. Some noises comes due to temperature. Some noises come due to the inherent surface defect or traps. This is like flicker noise. But there are some noise which is, let's say, the short noise, and if you remember, this noise was due to the source itself. So basically today what we are going to discuss is about the sources, what kind of different light sources we have, what kind of problems they possess, right? So we'll discuss in more detail about this. And this I have told you already, that if we reduce the intensity, we go into nanophotonics domain, but today what we are going to talk in mostly in the quantum optics domain. So when we look at the sources like this light beam, so this light beam has photons, the photon might be arriving from some point, right? So let's try to do one experiment, and let's try to find out what different kind of light sources we have. And remember that when we try to classify the light sources, what we have to do is photon statistics. Like, what is the statistics of this photons? Once we deal with this problem, or once we get to know about the type of sources, then next we can move towards the problems, what it possesses towards the detector. So let's first assume that we have a light beam. Okay, this light beam comes which has lot of photons in it, and this light beam is hitting to a photomultiplier tube, or let's say avalanche photodiode. So there is avalanche photodiode or photomultiplier tube, and a lot of photons are coming and hitting to this tube. As soon as photon comes and hit to this detector, we have connected a counter. So that's a time machine. It's there. As soon as a photon clicks, we will make a mark here that, okay, one photon has come. Similarly, as soon as the second photon comes, we make one more mark. So typically we call it time tagging. So what we are doing is we are tagging the each and every photon arrival. And this is being done using incident photon counter or time counter, and this we have attached to this APD or avalanche photodiode, so it will count the number of photons. And for example, this photon came, and after a very long time the next photon came. As compared to this, the first photon came and the next photon came very quickly, so we are tagging the time. Now suppose we have wavelength given for this light source, and power is also given. We have a 1 milliwatt source and we have wavelength there which is 620. Now if I would like to know how many number of photons are present, I can do the calculation, I can do the math, and I can find out how many number of photons are there, or average number of photons are there. So this n, this I can find out. So h is a constant, and mu you can write c by lambda. C is a constant, lambda is given here, right? So this power is also given, and average number of photons, we can find out this. And this value typically comes out 10 to the power 15 for these numbers. So this is, let's say, a 620 nanometer red color laser. So if you take a diode laser, which is simply a laser pointer, if you take that, which has similar sort of powers, and within a second, if you try to count, and you will find out that you have 10 to the power of 15 of these kind of lines, or there are 10 to the power 15 photons are there within a second. So this counter has to be very fast, that within a femtosecond it can count the photons. But finally a simple calculation can be done, and we can find out how many photons are there. But the question comes that then this laser diode, the laser pointer which we are using, it's a diode laser, can we use this as a single photon source? Because a lot of photons are coming, and what we could do, we can dilute this laser and we can try to get only one single photon from it. So will it become a single photon source? Second, you can think in this direction that, okay, in 1 second 10 to the power 15 photons are coming. So can I do something that maybe I can only catch one single photon? So let me use a detector which can detect things within a femtoseconds. So if you can detect things in within every 10 to the power minus 15 seconds, you can easily detect a single photon from this laser. So if I do this, then simply I can say that I have created a single photon source, because every 1 femtosecond I can now capture a single photon, and these photons are coming from this laser, so I have a single photon source. but typically that is not true. So we will also discuss this in detail, but up to now you know that if you have wavelength given, power given, you can calculate number of photons in 1 second. So per second, this is also the photon flux. Now what is the problem if you think about this, that why this detector is not able to detect these photons which are coming within a femtosecond? So the problem comes from the semiconductor side. So if you go to, let's say, any company's website and you try to purchase a detector, there are certain specifications which are given there, right? And one of the specifications is dead time of the detector. What do I mean by the dead time of detector? So let me discuss the dead time of the detector. So usually this dead time for current detectors which are available is roughly in microseconds. So you have detectors which has dead time in microsecond. What do I mean by that? So let's say this is the response of a detector, right? That's the response of a detector. So for some time duration, this detector is off, and for some time duration it is on, and then off again, and then on again, right? So as soon as a photon comes, it will be on, and then after the photon dissipates, goes into electron hole pair, goes into the circuitry, and then this will be off and then on again. Let's suppose that this detector is off for 1 microsecond, right? Now the question is how many photons this detector can detect within a second. So we would like to know the number of photons which it can detect, and this has to be within a second. So suppose this is your 1 second time frame from here to here, this is 1 second, right? Let's say the first photon comes and you detect this photon, then after 1 microsecond the second photon comes and your detector is able to detect it. But suppose if this photon comes even before that, let's say in 10 to the power minus 9 second, your detector will not be even able to tell you. And then this photon will be lapsed because it will not be able to detect it. And then similarly, the third photon, fourth photon, fifth photon. So within a second, maximum number of photons this detector can detect is 10 to the power 6 photons, right? Because every microsecond this detector is off and then it's on for 1 microsecond, and within a microsecond you can have maximum 10 to the power 6 photon. So that is the count rate of this detector. So if I told you previously also, so how many number of photons are actually coming in a typical laser diode? What we purchase is 10 to the power 15. So we have 10 to the power 15 photons which is coming, but the detector is only able to detect 10 to the power 6 photon. So it has a dead time. Now, what should we do so that we can somehow detect more number of photons, or somehow we can detect, go into the regime of a single photon? Like just by intuition, something should come up in the mind that what could be the solution for this very basic solution. So for 1 milliwatt of power, if these many number of photons are coming, what happens if I reduce the power? So if I make the power picowatt, then the number of photon will be 10 to the power 6 per second. So I found out one solution is that I should reduce the power of photons or the laser beam which I am using. Somehow if I use some neutral density filter or something, and then I close this or reduce the intensity of this laser light, then in a second 10 to the power 6 photons are coming, and now this detector is able to do the detection. One can also think that, okay, why not we can make a detector which has a dead time of 10 to the power minus 9 or minus 12 or minus 15. We can make a better detector. That could be the another solution. So that is also true. The another solution is also there. But currently the problem with the detector is that they have a dead time of 10 to the power minus 6. So you do not have smaller than that. What is the reason for that? So this is a semiconductor device, right? And you know that as soon as you apply negative reverse bias, there is a field here. And because of this field, suppose a photon comes, and then this is an electron hole pair generated. So the electron will travel here with a drift velocity, and this field will also support it. So it will take some time to cross this barrier. Then the next will be the diffusion velocity, right? So again, there will be some time associated with it. It is not like as soon as you hit the photon, and electron hole pair are coming into the circuitry within a femtosecond. This is not happening. Since it's a semiconductor device, here also it takes time, which is drift time, then the diffusion time. And you also know that here there will be positive charges, negative charges, there will be a capacitance C, and there will be some sort of resistor also. So RC time constant is also there, right? So there are different sort of time constant which is prohibiting us, and we usually have a dead time of 10 to the power minus 6. So up to now, all the semiconductor detectors, they have typically maybe maximum nanoseconds, but not beyond that. So that is the problem from the device perspective. But in order to overcome this problem, the solution is that you reduce the power or you go to picowatt. What could be the other solution? So this is the first solution. What could be the other solution if I want to detect smaller number of photons? So the first is to reduce power. Second is to play with the time, or you reduce the or you make the laser pulse laser rather than continuous wave. You have number of pulses coming, and these pulse duration is in your hand. You can make it smaller. So if very short pulse is coming, and then you are able to detect it. So let's see how that works. So here you have a intensity versus time graph. And this is how a CW laser, continuous wave laser, looks like, meaning the intensity is same all the time. But suppose if you have a pulse laser, meaning for some time duration the laser is on, which is showed with the blue color, and for some time duration the laser is off, and then on again, and then off. And this repetition rate is in your hand. You can control this repetition rate, meaning you can also control for how long the laser will be on, for nanosecond, for femtosecond. So you can control this pulse width for how long the laser is on. And there are certain parameters in this pulse laser. For example, the fluence, total energy inside one particular pulse. This also you can decide that how much energy will be there. So you can calculate just area under the curve, and then the total is there. So by doing that, suppose let's take a question and try to find out how we can do that. So for example, we have a laser with 800 nanometer wavelength. Similar powers are there. So milliwatts power is there, and the repetition rate is 100 megahertz. What do I mean by 100 megahertz? Meaning every 10 nanosecond, one pulse is coming and hitting to your detector, right? So if you do that, then what is the average number of photon in per pulse? So that will come out as 10 to the power 7. So that is the second way how you can reduce the number of photons. So the first way is to reduce in terms of power. The second is to play with the time, then reduce the pulse width, or in terms of time duration, reduce it, and then again you have less number of photons available. And from this, your simple detector can work, and then you can detect the photons. So I hope up to this point it is clear. Then now let's consider a laser, and the light is coming from the laser in terms of photon, and that's a 1 ev light. So energy is given, and a detector is there, and 1 nanowatt of light is incidenting on this detector, and detector has 100% quantum efficiency. Whatever number of photons is incidenting, all the photons are getting converted into the current. Now the question is, how many average number of photons are there in a beam segment of 30 centimeter? So up to now I just gave you directly the number of photons, but here we will try to calculate how many number of photons will be there in this given question. So everything is given to us, and we know that power is nh mu, or You can also say average number of photons into energy. Energy is there, 1 eV. Power is there, which is hitting to detector, is nanowatts. And there is 100% of quantum efficiency. So roughly 6.25 into 10 to the power 9 photons are coming per second. That is the average number of photons. But I don't want this number. What I want is how many photons are there in a segment of 30 centimeters. So this is the laser. And from this laser, light is coming out. If I make here a box of 30 centimeter, I just make a box of 30 centimeter. What I want to know is that how many photons will I see inside this? 5, 10, 10 to the power 5, 10 to the power 9. How many photons will I see if this length is 30 centimeter? This is the question. And up to now, what we know is that from this laser, every second, 10 to the power 9 photons are coming out. So here, if you put a detector for 1 second, you will measure 10 to the power 9 photons. That is what we know. So in 1 second, if 10 to the power 9 photons are there, how many will be in 1 nanosecond? So if I put the detector here, only for 1 nanosecond, I will detect roughly 6.25 photon. Remember, photon should be integer number, and 6.25 is average number. So it makes sense. There is no need to round it off to 6 or 7 or something. So 6.25 is correct because it's the average number. So here within a nanosecond, there is 6.25 photons are available, but still that is not the answer to this question. What we are asking is how many are there in a 30 centimeter line segment. So how long is 1 nanosecond in terms of length? So we can convert this, since we know that the speed of light we know, right? So in 1 second, light covers this much of distance, meaning we can also say photon covers this much of distance. So in 1 nanosecond, how much distance a photon is covering is 30 centimeter, right? So meaning 6.25 photons should also be available in 30 centimeter. So if I take a length of 30 centimeter, I should usually find roughly 6 photon within that distance. But this sounds interesting, that how 6 photon can be available. So let's say this is 30 and these are total 6 photon, 1, 2, 3, 4, 5, 6, right? Now if I, rather than 1 EV, if I take a 2 EV beam, so I increase the energy. So here not 1 EV, but I have made it 2 EV. So now the energy has increased. And now how many number of photons will be there? So we can do the same math, and what we will find out is that average number of photon is reduced. So now it's 3 photons. So within a segment of 30 centimeter, the same laser is there with 1 nanowatt of power, but the energy is 2 eV, and then we have average number of photons is 3.1. I told you photon is a quantized number, so but it doesn't matter. It should be integer, but there is no need to make it integer because this is the average value. But what do I mean by this when I say it is the average value? Because here I'm saying that in 30 centimeter I should show 3.1 photon, so which we know doesn't make any sense. So it should be some integer number. Then what do I mean when I say average number of photons? So let's try to see in the next slide. So now what I'm trying to improvise my setup. So now I have this laser, right? And in front of this laser, I have a 30 centimeter of beam segment. And I have a very high speed camera that every nanosecond I can click pictures, and I'm taking the picture with this high speed camera of this 30 centimeter of line segment. This 30 centimeter, I'm clicking pictures of it. And I would actually like to know how is the distribution. So up to now, what I have told you is that we have a laser, light, everything is given about the laser, wavelength is given, power is given, energy, everything is there, and the photons are coming out from this laser source. Now I have taken a line segment of 30 centimeter. I know how many photons are there every second. Now I know how many are there in nanoseconds, and I have also information that in 30 centimeter there should be roughly 6.25 or 3.1 photon, depending on the energy, should be there. So up to that I know, but Now my point is I have taken a camera which can click pictures with a very fast time, and then I can take pictures, and I would like to know how these pictures look like. So the very first picture, when I took, I found three photons. One was here, second was here, and third was here. And similarly, I was kept taking pictures. So for example, in the second picture, I did not find any photons. In the third one, I found four, and they were something like this. And what I did is that I took 10 pictures. So from 1 to 10, I took 10 pictures, right? And in the first one, the photons were like this. The second one, there was no photon. In the fourth, the four photons, they are like this. So I found the fourth one here, first one here, second here, third here. And I did this. So now you could see that you have actually 10 events. So the first event and then so on up to 10. You have 10 events. For each event, you have number of photons. So here you found 3, 0, 4, everything is there. And you can try to find out the average number of photon. Once you do this math, what you would see is that finally the average number of photon is 3.1. And if I go back to this question, if we have a 2 eV beam, then average number of photons in 1 nanosecond is 3.1. So actually we were trying to solve this problem, and you can see that this is the solution, that if you have 3.1 average number of photons, this is how I saw in my camera. But this is the first time I do the experiment. Suppose next time I do the experiment, I can find anything else. But the final crux is that the average number of photons will be 3.1. So next time if you do, maybe here there will be more photons, 5 or 10, whatever, but the average will always come out as 3.1. So that is the point I wanted to clarify you with these diagrams. So next, what I will do is I will reduce this length. So now from 30, I will make it 3 centimeters. So let me reduce the length of that. So again, the same laser is there. Rather than a 30 centimeter block, this time I will put only a 3 centimeter block. And then I would again, suppose I have again the same high speed camera, and I would like to calculate the average number of photons. So let's say in this case, average number of photons is 0.31. This we have calculated. We have lambda, we have energy, we have power. This we know that average number of photons is this much. And we have a very high speed camera of 100 picosecond. And again, we take pictures. And once you do that, this is what you find out, that in the very first picture, you have 0 photon. Next one, you have 1. Then third one again 0. Then fourth one again 1. And so on, 0, 0, 0, 1, 0, 0. That's what you found out. And if you take the average of these, just sum up and divide, what you will end up is 0.31. What do I mean by that? So that is a powerful statement, meaning if you do the measurement 10 times, there is a probability that only in 3 occasions you are going to get a photon. That is the meaning of this average number. And that is very important, that in the 3 centimeter line segment, the number of photons available is only 3 if you do the measurement 10 times. Now we can do the same experiment, we can repeat it. Let's say now we have even faster camera. So this was 100 picosecond, now we have reduced it to 1 picosecond. So an average number of photons is 0.0031. That is the average number of photons. Now with this, we can make again this kind of statement, okay, that in how many occasions how many photons will be there. So what do I mean by that is that if I do 1,000 times of measurements, right, then there is only probability that we can detect only 3 photons. So multiple pulses are coming and I don't detect anything, and then out of these many pulses only 3 photons I'm going to capture. That is the simplistic meaning, that if you have a segment here and a laser source here and light is coming and you put a detector here and you will not see anything. 0 0 0 will keep coming out of thousands. Only 3 times your detector might trigger. So if you put a 3 centimeter of block here in between, this is what going to happen with the average photon number of 0.0031. And in some other lectures, you might have heard about the correlation function, G2 measurements and all. So this is what basically actually happens, is that you are trying to find out the statistics, that how the photon distribution is going to be within this particular line segment. Now you can make this segment smaller or bigger. You can talk about 30 centimeter length scale, and then suddenly this will become for out of 100 measurements, and then you will have only 0.3 photons available. So that scaling you can do, that is no problem. But now let's try to do this again one more time. So now suppose I have a 30 centimeter length, right? This is what we are using. And the question is where I can detect the photons out of this 30 centimeter. So out of this 30 centimeter, let's say I have 4 photons, so they are here, 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 and here, or they are maybe equally distributed, 1 2 3 4. So where means we are talking now about the location of these photons within that line segment. So that is the next question we are posing to ourselves, that okay, at which particular location these photons are there. The next is at what time instance these photons are getting detected, and what is the distribution of these photons. So we have a laser source and we know average number of photons, and we are trying to get the distribution of photons. And this is what in the beginning I told you, we are talking about the different type of sources and we are trying to get the photon statistics. So with the laser, a lot of photons are keep coming, okay, and then we have this segment of 30 centimeter. Let's say I detect 3 photons like this. One is here, second photon is here, third photon is here. But in the next time when I do, I detect 3 photons here. So now I'm puzzled, like, okay, can you now tell me, when I take again 30 centimeter of line segment, do you know where these 3 photons will be? What would be the location? Usually we don't really know. The location can be anything. They can be equidistant, or they all three can be at this point, or all three can be at the beginning. So then how are we going to know that where these photons are? So this is the very first time we are encountering in this lecture, is that the time instance when photons are detected is random. So we don't really know when we are going to detect the photons. So suppose you have a detector in this line segment. For time being, you can now consider this as a detector, and then within this detector you don't really know when the next photon is going to come. So you know average number of photons, but you still don't really know when the next photon is going to detect. So that is random. Now if you remember previous lectures, we talk about this, that why this randomness is coming into the picture, that the photons are coming from this laser. The first photon came, hit the detector, but when the next one will come, we don't really know about this. So inside this laser we usually have a gain media or gain material, and this gain material is typically a semiconductor. And once we have a semiconducting material, we have conduction bands and valence band. Now first inside the laser we have to build up, so that the beam can come out, stimulated emission can happen. So more number of electrons should be here in the excited level as compared to the valence band. So for that you have to do a lot of pumping. So when you do pumping, meaning this band gap is there, Eg, and you come up with the photon, and this photon is getting absorbed, and then electron hole pair is getting generated, right? So this particular state, so once it is absorbed, this will go up, electron will go up and it will stay there, right? Suppose this is a conduction band state and it has some lifetime, let's say 10 nanosecond. So meaning an electron can stay here for maximum of 10 nanosecond, and within 10 nanosecond this electron has to come back to the valence band, or it can go to any other defect state or somewhere else. But typically, idealistically, let's say this can stay here for 10 nanosecond. And now within this 10 nanosecond, you don't really know when is it going to come down. So if the lifetime is of 10 nanosecond, it can come down. Let's say the first electron come down and a photon emits within a 2 nanoseconds. The next same thing will happen next, maybe in 8 nanosecond or 3.2 nanosecond. So this is not in our hand. So this process itself is spontaneously random actually. And this creates a problem that the photons which are coming out is random. So that is the randomness which is due to the source itself, and it is inherent. Similarly, for example, the absorption process itself is random. Um, so this PN diode, the photons is incidenting on top, even though you put an anti-reflection coating or whatever, but usually what happens is that some photons will get absorbed and some will get reflected or might get transmitted. So you do not really control this, that which photon is getting absorbed with 100% probability. So there is no 100% probability. This process is random. Similarly, when the electron will go down to valence band and emit a photon, this process is also random. And since this is random, this gives us uh, randomness into the photon arrival. So I hope that is clear to you. Now this was about the time, at what time instant. So this we know, okay, this process is random. That time arrival we don't know, but what about the exact location? So if we fix a particular line segment which is 30 centimeter, can we tell, okay, this might be the distribution of these photons? So what is the distribution of these three photons in 30 centimeter? So again, let's go back to the same problem, that we have a laser, and now what we want is, we want the distribution, that how the distribution happens. And in the previous examples, what we have done is, always we know the power, and once we know the power, we have calculated the photon flux, or how many photons are there every second. So that value will be P divided by h mu, right? Now, previously we were considering a 30 centimeter line segment. Now what we can consider is a generalized way. So we have a line segment with the length L, and this number of photon within this beam segment will be how many? This we have to calculate. So again, this we remember, okay, that within 10 to the power 8 meters getting traveled within a second, then this you can call it as c. So this much of distance is c, right? So in 1 second you have number of photon will be 5, and this 1 second is length c is the number of photon which is 5, and if you divide 5 by c and multiply by L, that you have total number of photon in the length L. So I hope that is clear, because that is the, in the 1 second you have number of photons which is 5, because that is by definition photon flux is number of photons in a second. And how much is 1 second? 1 second is equal to the c. What is c? C is the 3 into 10 to the power 8 meters, which is equals to the 1 second, because that much of the distance is getting traveled in a second. So in terms of length scale, we can do the math that in the length scale c, number of photon is 5, because in the 1 is 5, then 1 second is equal to the c. And if you want to calculate for L, you divide 5 by c, multiply by L, and that is the average number of photon in a line segment of L. So that is the total number of photons now we know in the phi L by C segment. Now what you can do is, you can further divide the same line segment which was L, you can further divide it into capital N. So make small subsections and then try to find out how many photons are there, because what finally we are trying to get is the distribution. And if we know within this small location what is the probability of finding a photon, we can tell the complete distribution. So that's why we have divided this total L in capital N segments. So once you do that, the probability of finding a photon in one of those, So for example, this is total L, you divide it in N, the probability of finding one photon in one of this is given by average number of photon divided by the total number of segments what you have created. That will be the probability to find the photon here, right? Now we are looking for the probability of finding one photon, but what is the probability of finding n number of photons? So this n can be anything. The probability of finding 2 photon or 4 photon or 10 photons, this can be anything. So for this, remember this picture, within the line segment of 30 centimeter, the probability of finding 3 photons, right? The probability of finding 0 photons, the probability of finding 4 photons. So if we can somehow draw the same picture in terms of a graph, meaning we have created a distribution. And that is what I was trying to do here, right? That we are trying to generalize these pictures, because previously we have taken some example that this much is the length, and if this much is the length, this much is power, wavelength is there, and how many photons, average photons are there. Then if you take different pictures, how many photon will be distributed, how. So we are trying to do the same story here, and but this time not for some specific number, but this time for generalized way. And for in general, if you do that math, what you will find out is the probability of finding n number of photons will be given by this particular formula. So that is the probability. But what I'm doing is I'm tending n towards the infinity, meaning I have created small segments which are very tiny. So if that is tiny, the total number of segments is going to infinite. Once I do that, meaning the time interval is very short or I'm taking pictures very quickly, the probability to finding n number of photons in a beam segment of L by n is given by this particular formula. This is n factorial. This is n bar, meaning average number of photon to the power n exponential minus n bar. And typically we call this as a Poissonian distribution. So we can try to plot and see how this distribution looks like. And here remember that this n probability of finding number of photons, so this has to be integer, probability of either finding 0 photon or 1 photon or 2 photon. So this n has to be integer, this cannot be 1.2 or something. So if you look at this, this is how it looks like. So it will be a Poissonian distribution, this, right? And that's how this distribution looks like. This is the formula by which it is given. Just to look at one example, let's say we have average number of photons 1, right? So n bar is given to us, n bar is 1. So this quantity n bar is 1. Now what you can do is you can try to find out probability. So in this graph, this is the probability here. On the y-axis and x-axis you have number of photons. So tell me, what is the probability of finding 0 photons? So the probability of finding 0 photon is roughly 0.4, let's say. What is the probability of finding 1 photon? So probability of finding 1 photon is again the same. Then probability of finding 10 photon. So this is tending towards 0. So probability of finding 10 photon might be 0. So if mean or average number of photon is 1, then probability of finding 10 photon is 1. Now you can do this as a mathematics also. So you know n bar, which is 1, and suppose what you want is p0, meaning what is the probability of finding 0 photons if I have average number 1. So you put this n bar here. So n bar is 1 and n is 0, right? N is 0. So all the values is given to us. N bar is given in this formula and n is also given. So if you do that, 0 factorial is 1 and this is e to the power minus 1. So the probability of finding 0 photon will be 1 by e. And e is 2 point something, and this is typically what is there on this formula. So 0.34 or something. So that is the probability of finding 0 photon. Similarly, you can do the math for finding 1 photon. So here now n bar remains the same, but n value has changed and now n value is 1. You can put in this formula, 1 factorial is 1 and this again is e to the power minus 1 and this will be 1. So again, that also you see in this, that probability of finding 0 photon or 1 photon is same. Now you can look into this in this way, that if average number of photon is 1, then what will be the probability of finding 20 photon or 50 photon? Because it should be very low, right? Because you see that if suppose in one line segment you already find 20 photons, then in other line segment definitely you should have 0 0 0 multiple times, then only the average value will be 0 plus uh, 20 occasions. If you keep doing and then divide by 20, then only you will end up with 1, right? You will keep taking multiple segments, and within the first segment if you get 20 photons, then all other 19s you have to put 0 0 0. So here 0 0 0, and then you can divide by 20, and the average comes out as 1, right? So that means the probability of finding 20 photons in this line segment will be very poor, or even to find 100 photons will be very low. Same you can also prove by putting here n bar is 1, take n equals to 20, and it will come out that this value will tend to 0. So what you could see, that this kind of Gaussian distribution is something like this for small n bar values, something like this. So if this n bar, average number of photons, is lower, this looks like a Gaussian curve with a long tail, but it's not Gaussian. But if you increase the n bar, average number of photons, for example from 1 to 10, then this curve looks more like a Gaussian curve. So Poissonian distribution is a long tail Gaussian, and this kind of distribution is shown by the light source, a typical light source, which is laser. Now there are multiple parameters to this. For example, if you have this plot, which is the Poissonian distribution, what is the, so this distribution is there, what is the mean value? So this mean value of this distribution will be average number of photon, n bar. So that is always the n bar. What is the deviation? This you can find out, and the variance. So there are three important terms. One is mean, one is standard deviation, and one is the variance. And variance is nothing but the under root of standard deviation. So standard deviation is under root of the mean value. So this you can find out the standard deviation in this. And for the Poissonian case, for this particular case, if you look at this standard deviation, this will be equal to the under root of the mean value. So that is the typical feature of this Poissonian distribution, right? So up to now, I hope it is clear to you that, okay, if a light source is given to us, we can define the photon distribution, how the photons are distributed, and depending on that, we can say that, okay, if it is a Poisson distribution or not, using this formula. And intuitively also I tried to explain you with different kind of line segments. So what I was trying to paint a picture, because directly doesn't make sense to jump to this formula, because you should get a little bit feeling of it, that how we are trying to build up towards this formula. So I did not derive it. The formula itself is there, but we just try to find out the meaning of it through different diagrams. So depending on distribution, I told you that we are discussing about the distribution of the light, so photon distribution, and depending on the photon distribution, we are going to tell what kind of light sources we have. So that is the typical curve shown here. So again, here is the probability of finding number of photons, and here is the average number of photons. If we have a Poissonian distribution, which is shown something like this, then this deviation is equals to the under root of mean value. If a distribution is super Poissonian, meaning the spread is more, so here the standard deviation is bigger than the mean of average value. And in case of sub-Poissonian, it is smaller. So there are three kind of light sources. The first light sources which follow Poissonian distribution, this kind of distribution. They are, for example, laser light or coherent light sources, and they always follow Poissonian distribution. The second kind of light sources we have is super Poissonian light sources, this kind of light sources, this one. And for example, all the thermal light source or incoherent light sources, For example, LED light bulbs or tube light, they follow this kind of distribution, or one can also say Bose-Einstein distribution. The third is sub-Poissonian distribution. So typically, classical light sources, they don't show this kind of distribution. So there is no classical analogous to it, and typically all the quantum light sources, they have this property that the fluctuations are smaller than the under root of mean value. So that is the main property. So suppose if you are trying to build a quantum light source, this is the first property you can try to prove that you really have a quantum light source. So I hope it is clear that depending on the distribution, we can make a probability distribution of photons, and depending on that we can classify the light sources. And there are three major type of light sources: incoherent, coherent, and quantum light sources. And the quantum ones, they show sub-Poissonian distribution. um, when we look at the photon arrival picture, so this is how it looks like. So for quantum light sources, what are the quantum light sources? So if you remember, in one of the lecture I have told you some properties of a single photon source, and there are a lot of things. For example, SPDC based light sources or quantum dot based single photon sources, 2D materials, they all act as a single photon source, meaning they are in the quantum regime. So they are showing sub-Poissonian distribution, this kind of distribution, right? How this distribution looks like in terms of that photon picture. Suppose I take a 30 centimeter line segment and I have a quantum light source here. If I click a picture, how the photons distribution will look like. So this is how the photon distribution will look like, that there is very less fluctuations, meaning the distance between two consecutive photons is equal. And these are called anti-bunched light sources. So sub-Poissonian or anti-bunched, it's the same kind of behavior. And this is how the photon picture is, that there is, so in this case the fluctuation is quite less because the determinism is there, that the next photon, you know that within this much of time the next photon will be arriving. That is the quantum light source. Next, we have coherent light sources, and they are random arrival. So I told you that we have this conduction band, valence band, and the inherent nature is there, that the photon arrival is random in nature. And these kind of light sources is typically laser light sources. So laser light source have this kind of photon distribution. So if you know that one photon is there in your time tagger, next photon comes, third photon comes, even if you know that, you cannot tell when the photon, fourth photon will be coming. It can come at this time or it can come after some time delay. That is the property of random light source or coherent light source. But remember, there is one important thing, that the average number of photons is always fixed. So what do I mean by that? In the beginning, I told you, let's take a 1 milliwatt of laser with 620 nanometer and 10 to the power 15 photons are there in 1 second per second. So in this case also, if you look at the average number of photon within a second or within 5 minutes, the average number of photon will be fixed. That will be 10 to the power 15 in coherent light sources. This is not going to change. What is going to change is that if you go in a smaller scale, minute scale, and then you will see, so just from 1 second you move first to millisecond to nanosecond, and once you go there, then you will see that okay, first photon is coming, I do not know when the second is coming, but within 1 second combine, I know that total 10 to the power 15 will be there, but still you cannot tell when the second photon is coming. So in my previous lectures, I have given you example of rain, right? So if you look at the rain at a very small time scale, first drop is there and the next drop you cannot tell where will be the next drop on the ground. But if you look at the whole scenario within a 4 or 5 hours of time frame, you can tell that in this region there was less rain and in this region there was a bigger rain or more rainfall. But the same happens in the coherent light sources or Poissonian distribution case, is that if you go with the very small time scale, you cannot tell when the next photon is arriving. But on a bigger time scale, the average number of photons is there, which is fixed. The third one is the bunched light source. Here the photons are coming at a bunch, like four photons together, they are there, and then there are no photons. And then there are a bunch of three or four photons. And this kind of light sources are chaotic light sources or thermal light sources. So that's again the same distribution of light or photon arrivals. In terms of photon arrival, previously this was in terms of a graph distribution, and here we see the same thing in terms of a line segment and photon picture. So anti-bunched light source, quantum light sources, coherent light sources are usually lasers, and bunched are thermal light sources. So that is the overall distribution. I hope up to this point it is clear to you. And now you will understand why you are having this quantum limit to the measurement. Because now you know that in your coherent light sources, already there is a limit that the photon arrival is random. Now you can think from the photodiode perspective. So suppose there is this photodiode. Always we are considering this classic photodiode picture, P and N side, and putting in the reverse bias. And we hit this photodiode with photons, and remember that photons are coming from some light source, and they are bringing the characteristic of that light source. So whether they are coming from anti-bunched light source or they are coming from bunched light source, and that same characteristic will be carry forward. So they will bring that characteristic, and together with that characteristic they will hit to this detector, right? So let's suppose that a coherent light source is there, and this light source is hitting to this detector. Now what I'm going to do is I'm going to make a xy graph. In the y-axis I have photons, and on the x-axis I have time. So with time, what I see is that this is the pulse train of photons. So that's how the photon arrival is happening. And with this photon arrival, the photoelectrons will also be generated. So for example, for this photon, this electron hole pair is getting generated, right? For this photon, electron hole pair is generated. For this photon, maybe this got reflected. So this photon was not even absorbed. So there is no point of saying that a photoelectron is getting generated. So there is no photoelectron for this, and then same goes on. Maybe for this, the photoelectrons got generated, but they got trapped or they lost in terms of heat. So there is no photocurrent, right? So this photon randomness is now converted into the photoelectrons. Okay, and now this photoelectron will serve as a current pulse. So finally you will get a current with this photoelectrons. Once they go out in this circuit, they will generate the current value. So maybe for this photon you have now current. The next photon you don't know when will be the next photon, but whenever it comes you will have a current pulse. And then for third, maybe it got reflected, you don't have a current pulse. So what do you expect? Do you expect your current response with time like this, or do you expect that first there is a current, and then maybe for the next photon arrival is random, it doesn't really arrive after some time, and then it comes? Okay, then there is current, goes back, then next photon comes after some time. Okay, and then there is a current, then comes, then next photon comes very quickly, so there is current, then next photon comes again very quickly, but then next photon comes after some time. So this statistics of photons is now getting transferred into the current pulses. And since our current pulse is not like this continuous pulse, but it is a up down up down up down with random fluctuations, and this randomness is decided by the Poissonian distribution. So because of that we have some sort of noise in our system, and that is the noise which is inherent. You cannot do anything about this noise. So for example, at high frequencies we have this short noise, and typically we call this same Poissonian thing as a short noise, and that is the total power of this short noise. So for example, this current which is random, right, and that is the average, this dotted line, this is the average. So what is happening is that you have this current which is not like this, but it is typically like like this. Now what you can do is you can actually plot a graph like this, and you can see this much is the variance, and this variance or standard deviation is the under root of the n bar, which is your average number of photons. So if there is more fluctuation, this will be like this, but depending on the short noise or Poissonian distribution, you can calculate how much will be the fluctuations here. And this is called the short noise into your system, and this short noise is the characteristic of your photon arrival, and this photon arrival is the characteristic of your source which you are using. So it will always be there, right? And how much will be this short noise? So if you calculate or compute in terms of formula, this will be 2e delta f I RL. RL is the load resistance, delta F is the bandwidth in your system, E is the charge of electrons, and I is the average current value, meaning this average value. Or you can now try to make a connection with the graph or with the line segment. So in the line segment, we were calculating average number of photon, showing it like this. So this same average number of photon is now converted into current, and that is the average value we are talking about. So if we plot a line of average, so that will be this average here. So you have to put this value here, and then you can calculate your short noise. Now the short noise behavior we see as terms of frequency. So for example, at very low frequencies, the noise which is dominated is classical noise. For example, flicker noise is very dominant of 1 by f noise. F is small, noise is very high. Short noise is always there, right? But what happens if short noise is there and your signal is also there, and if your signal is very weak, you have a hard time finding out whether you are calculating a signal or a noise. So the aim is to go below the short noise and limit here in this region, and 1 by tau d is your dead time of the detector. So here after this your detector will not respond, so you have to play within this region in order to work below the short noise limit, right? Because above that your short noise is going to dominate. So for example, how much is this? So SNR for a short noise system is given by, like for example, this is your signal and this is your noise. So your short noise is under root of n bar, which is the standard deviation, and n bar is your mean. And remember that for the Poissonian distribution, this is how it is given. So if you do that, finally your SNR is under root of n. N is the average number of photons. So this is called the short noise limit, meaning you have to go below this noise in order to calculate your signal, because if you are measuring at this, you are not going to detect. And let me give you an example, just a very simple example. We try to understand this. What is the meaning of short noise limited system or measurement below short noise? So let's say number of photons coming is given here in this column, and the short noise is given here. So for example, suppose we have 100 photons. The formula is under root of n bar. So if average number of photons is 1000, the short noise will be 33 roughly. Now let's try to reduce the power, or let's try to play with smaller intensities. So suppose if you have only 100 photons, then the short noise will be 10 under root of 100. Now suppose you have only 10 photons, then the short noise will be 3.33. Now you consider this, that as compared to 1000, 33 is nothing, right? But as compared to 100, 10 is a bigger number, right, in terms of percentage. And here if you see roughly 33%, so here maybe only 10%, here suddenly 33% of your signal is noise. Now what happens if I make only one single photon? So under root of 1 will be 1. So then my SNR will again be 1. So I don't know whether I'm measuring a signal or I'm measuring a noise, right? So when you try to work with a smaller number of photons, what your system is always, you have to find a way to measure below the short noise limit. So that is just one example, just to make sure that what is the implications when you go with the lower power, how the short noise impact the system. So short noise becomes very dominant. Here 33% of signal is your noise. So you have to find a way to measure below the short noise limit. Now let me take a break of 5 minutes, and then we proceed after that.
Sure, sir.
So let's begin the lecture about the linear detectors and quadrature. So, but I will carry forward from the previous problem itself. So we were discussing the short noise, and we know that at a very small or low number of photons, the short noise problem is quite dominant. But when we talk about the noise, so what we have to see is that, for example, this is the photodetector. We always use this, and that's the incident photons or the power of the incident photon, which is P in. The electron hole pairs are getting generated and the photocurrent is getting introduced. Now, the definition is this, that photocurrent is equal to the responsivity into the incident power. This we know previously. And we also know that this detector is typically responding to the intensity. What is the intensity? Is the amplitude of the electric field. And because of that, we call this as a square law detector. So typically, if you go into a laser lab, you shine the laser on a photodetector, what the detector will tell you is that you have roughly a power of milliwatts or something. But the detector will not tell you for which wavelength this power is there. So the power can be uh, for example, the wavelength can be 400 nanometer or 450 nanometer. So for a particular wavelength range, a detector works very good. If you change that range, it will change. It will not change you. For example, if you just change 10 or 20 nanometers, so it will not tell you what was the wavelength of that incident light. The second important thing is that it will not tell you the phase. So what was the phase of that light? So for example, the light was this kind of pattern was falling on the detector, or this kind of pattern was falling on the detector. This is the simple photodiode is not going to tell you, and because of that, because it responds to the amplitude electric field, so that is what we call as a square law detector. The the important thing in the detector is that we have to take care of these two important noise, which is the thermal noise and short noise, and these are the formulas for this noise, right? So for short noise, we know that we have seen it. 2q is the charge, and I is the total current, which the value is given here for this photocurrent, and delta f is the bandwidth. What is id? Id is the dark current. So, for example, if there is no extra light inside that room where the photodetector is, we can consider this as a zero. But if there are more photo, just because of some other light sources or ambient light, if there is current, then we call it as a dark current. This sigma square T, or the variance of due to the thermal current, is given by this particular formula, right? So this depends heavily on the temperature. Now let's try to calculate how much of each of this power, like thermal power or short noise, how much is that? So consider that we are working at a room temperature. We are trying to find out the noise. So the same, we can consider this as this formula at room temperature, that this is totally dependent on the load resistance if the room temperature is there at. And if you put some load resistance, for example 1 kilo ohm at 10 gigahertz, so the noise will be roughly thermal noise current will be 0.4 microampere. So that will be the thermal noise. We are just trying to get an overview how much is the, and then later I will make a analogy with this. So but for the time being, let's just try to find out how much is the thermal noise current. So that is roughly 0.4 microampere, right? For a load resistance of 1 kilo ohm and bandwidth of 10 gigahertz. What happens if you try to find out the short noise? So again, you have responsivity RD is 1.2, same RL is 1 kilo ohm, and for 10 gigahertz system, you try to find out. So you have the detector, and roughly 1 milliwatt of power is incidenting on the detector. So this is a quite huge power. Typically, when we talk about quantum, we work with the very small power, but let's say we have very large power which is hitting on the detector, and if you try to calculate the short noise, this you will end up with 0.4 microampere. So for a large power, typically come up in the same range. But if you reduce the power, you talk about the real power what we have at the detector. So suppose you have a laser source. Just after the laser source, you have in milliwatts of power. At the detector, you have to reduce it because it will couple through fiber, or even if it goes open space at the detector level, you roughly have this much of power. And if you have this much of realistic power at the detector, the short noise is 0.02 microampere. So typically this short noise is lower as compared to your thermal noise, right? Just giving some example, reference example. Now what we have to do is we look at the signal to noise ratio of a photodiode. What is the signal to noise ratio? So what is the signal? Signal is this photocurrent, right? Photocurrent is how much is the responsivity into power input. And we can, since it is the square, so we can do the square. Now the noise, what is at the noise? So we have two type of noise. One is the thermal noise and second is the short noise, right? That's the formula for the short noise. So this I plus ID, where I is simply written as P into responsivity. And this is the SNR for any, let's say a pin diode we have taken. For the pin diode, this is the value of the SNR, right? And we also know, just now we calculate, is that typically thermal noise is higher, which is in 0.4 microamp, and short noise is lower for a lower incident power at the detector, which is 0.02 or something. Now typically, there are two regimes in which detector works. One is the short noise limited regime. Previously also we talked about that in the quantum system, we have to work with the short noise limited cases because the source itself is giving a noise in the arrival of the photons. So, but in general, a diode can be having two regimes, right? One is the short noise limited regime and the second is the thermal noise limited regime. So as the name itself is suggesting, meaning thermal noise is limited the system. So thermal noise is too much and we cannot overcome the thermal noise, and that is limiting our system. That is called the thermal noise limited systems. Similarly, here the short noise will be more, or it will be limiting us to measure something. So that is called the short noise limited regime, right? So what do I, for example, if I talk about thermal noise limited systems, what happens to SNR? So meaning thermal noise is more, right? This noise is too much and this noise is small. So we can discard this value, complete value. And in case of thermal noise limited system, when we talk about SNR, we talk about the top part, right? And this value, because that is the major component of noise which is working in case of thermal noise systems. And then sigma t you can expand because we know the formula in terms of 4kt, right? Similarly here in case of short noise limited systems, right, that is the signal rd into pn, this we know. And in case of short noise limited system, short noise is the one which is creating the problem. It is higher in terms of power and the thermal noise is not there. So we have somehow suppressed the thermal noise, but short noise is there. And since for idealistically we can consider id equals to 0, so one rdp is cancelled with one rdp and you have something like this. So that is your snr. Now if you look at this, so here your snr is directly related with the incident power. So with the incident power, if you already know that if you reduce the power, the short noise will be getting reduced, right? So here with this you can see that. And in case of thermal limited system, this is how the system behaves, or basically RL is the one which is the defining factor. So for example, now this is for a simple diode, right? Pin diode. Now let's talk about avalanche photodiode. So what will change in case of avalanche photodiode? So usually it is exactly the same. It's just that in avalanche photodiode you have a ion multiplication factor, or for a single photon arrival there will be multiple electron hole pair will getting generated. So you just have one m, a multiplication factor with m is there in terms of responsivity. So total current will be multiplied by m square. This will be extra. And when you talk about the short noise, so this is the short noise, and for your thermal noise, this is not going to change. So this formula will remain like this. Now again in this detector, if I talk about two particular cases, what is the short noise limited case and what is the thermal noise limited case? So if I try to do that, so I told you in the beginning itself, in case of short noise limited system, short noise is the one which is creating the problem. So what we can do is we can remove this term from the denominator, because thermal noise is not doing any problem. How we can do that? So we can take down the temperature of your whole system to very low temperatures. This is what typically people do by nitrogen based cooling or helium. And if your system is dominated by thermal noise, meaning thermal noise is high, and in that case you have to reduce this number. So let's try to see each one of this one by one. So let's say your system is in the thermal noise limited case, meaning this noise is going to zero, right? So this is the noise which is creating the actual problem. And if you now try to calculate the SNR as compared to this, your system is improved by m square, right? Because this m square is extra term here as compared to this. In case of short noise limited systems, what you can do is you can discard this value, because thermal noise somehow you have managed, but short noise is still there in the system. Now here, this m square will getting cancelled with this m square. So in short noise limited case, the SNR is degraded with the value of FA. So there is extra term at the denominator, and your total SNR will get degraded. It will not get enhanced, right? So in thermal noise limited system, the same APD is getting more advantage by giving you more SNR. But as compared to PIN, if you use the APD in a short noise limited system, that is degrading your SNR. So it depends that in which regime you want to use your APD, right? And let me show you a graph in order to make things more understandable. So suppose we try to create a graph between, here we have noise variance or all different kind of noises, which is on the y-axis, and input power, which is on the x-axis. So what we see here is that this is the short noise term, right? And this is the thermal noise term. If you look at the thermal noise term, this is not dependent on the input power, this is dependent on the temperature. So typically your thermal noise will be a constant value, right? What happens to the short noise? So if you increase the input power, the short noise is going to increase, right? So that is your short noise, which is going to increase by increasing the input power, and because that is what the formula says. Now here we have the cross section where both the things are intersecting with each other. Now we have two regimes. One regime is this and one regime is this. So we have to distinguish which regime is what. So if you look at this particular regime, here you see that this is your thermal noise, which is higher than your short noise. So here you are limited by the thermal noise because your thermal noise is more. So that is called the thermal noise limited case, this particular case. And this particular case, you have more short noise. So short noise is creating the problem, and that is called the short noise limited case. So depending on your input power, you have two different cases, right? And with higher power, what you have is typically short noise limited cases. Now, how do I get my detector to operate in short noise limited regime, given that my signal power is very low? So previously what you have seen is, given power is very low, then typically you operate in this regime, right? Because here you have input power is quite low. And if the input power is low, short noise is less, but thermal noise is quite high. And this is called thermal noise limited system. But typically what you want to operate is short noise limited systems. But your signal strength is very low. Now your signal strength is low, meaning you are using very small number of photons, so 1 photon or 2 photons. This is what you're talking about, right? And since this arrival of photon is also giving you short noise, and you are limited with that, and you want to measure below that short noise, so what is the option, how you can increase that? So now again, look at this particular formula, right? And what you want is to want to increase your input power, but nobody is telling you that this extra power should come from the source itself, right? Or from the signal itself. So what you could do is you could attach something extra so that your total input power is getting increased. So for example, let's say here we have a beam splitter, so meaning a component which splits light into two, 50-50, and from this part your signal is coming, which is very weak. But your signal is weak and you want to operate in the short noise limited regime, and for that you have to increase your power, then only you can work in the short noise limited regime. So what you do is you introduce one more extra term. In terms of optics, you can call it a laser, and this laser has similar frequency what you have here, but very high amplitude as compared to your signal field. Once you do that, in terms of electronics, you could say that you can put an oscillator, and this oscillator is having the same frequency what is your signal, but your amplitude strength is quite high. Once you do that, when these two combine, finally the total strength which is detected by your detector will be signal plus this local oscillator. Because this is a square law detector, right, it will only respond to the electric field. So your detector, this will be the total photocurrent, and that is the basic idea of a homodyne or heterodyne detection, or you can also call it as a coherent detection, meaning that you put one more extra oscillator and then you try to boost your signal field, and by doing that you can finally do signal plus local oscillator, and that will increase your signal strength. And this technique is overall called homodyne, and if this frequency is a little bit different, then you can call it as a heterodyne detection. And this is typically easy to use, let's say in terms of electronics, but in terms of optics it is not that easy to create a laser source which has typically the same frequency as you are having in the signal. So what kind of technique people use and how differently this can be done, this we will also discuss. The another major advantage of this detection is that you can detect your frequency and phase. So I told you in the beginning that simple photodetector, if you put a laser in front of it, it will just give you the power value. It will not tell you at which phase the light is coming. But using this homodyne and heterodyne detection, you can do the phase detection as well. And with this, we will see what is the meaning of quadrature and all that. But just very simply to explain you, for example, you have a signal field. So that is very basic in electronics and communication. Let's say you have a signal field which is given by this, right, where omega is the frequency and phi is the signal phase, right, and that is the amplitude. And you have a local oscillator which is given something like this. So you have a signal which is low strength, and then you have a oscillator which resonating at the same frequency. Phase is different, and this ELO is quite high, right? Now what your photodetector is responding is to signal plus your local oscillator. Once you do that, you take this and a plus b whole square, you will end up with something like this. Now remember that this term is DC term. This is also a DC term. This is the only term which is the AC term. And this term is depending on the I is directly proportional to the ES, not ES square. Because up to now, this was depending on the ES square or square law detector, right? Once it is directly depending on the local oscillator or signal strength, we simply call this as a linear detector, because now it is linearly proportional to the strength of your signal. So that is why it's called the linear detection. So that is the very first thing what we have to consider, is that simply the photodiode is a square law detector, but as soon as you put it together with the local oscillator and try to do coherent detection or homodyne heterodyne type of detection, it becomes a linear detection. Okay, that is the first thing. Now we take the same problem again. So again we have a, let's say a signal field which is given something like this, where a is the amplitude, again omega is the frequency, and phi is the phase. And some, let's say you have a local oscillator or some extra signal which is cos omega t, and you multiply this signal with the cos omega t. Now the simple mathematics you can apply, and what will happen is that there will be a low frequency term and then there will be a high frequency term, right? So if you multiply this with this, you will end up with something like, so if you do the filtering here at this term, low pass filter, if you apply, you will get a signal which is a by 2 cos phi, right? Let's just name it as a signal I. So up to now, what we have done is we have a signal which is a cos omega t. We multiplied simply with the a cosine, and what we ended up is a by 2 cos phi, where phi is the phase of this signal, right? Now, next time, rather than cos omega t, multiply the same signal with sine omega t. Let's just simply do that math. Let's see what comes out. So this time signal, so you can again do like what you do 2 cos a cos b, the same formula you can also apply for 2 sine a cos b, and this is what you will end up with. So that is the final term. So you have a signal which is I, a by 2 cos phi. The second one is a by 2 sine phi. Suppose you have these two, what you could do? You could do I square plus q square. If you do that, you will end up with the value A. So you can calculate value A. What is value A? Value A was the amplitude of this signal. So first thing I can calculate is amplitude. Second you can calculate is tan inverse Q by I. So you can also calculate the phase. So if I look back what I have done, so a signal was given to me. I multiply this signal with cos and sine. And with these two multiplications, I got two different signal. One was this, one was this. And by this, I was able to get amplitude and phase. Now, what is cos and phi? So if you try to see, this is cos and this is sine, right? So sine and cos is 90-degree away from each other. So if you do sine 90 plus theta will be cos theta, or cos 90 plus theta is sine theta. So if two things has 90 degree of change, they call it as a quadrature. So x here, suppose this is x, and if this is y, they both has a 90 degree of phase difference, then we call them as a quadrature. That is the very general representation of quadrature. Now this quadrature can be anything, but what we found out that in electronics, if we take two signal which are quadrature to each other, so for example cos and sine, and if we multiply this to a signal, then we can find out the phase and amplitude of that signal. So that is a powerful technique, or this is called the quadrature measurements. That by measuring the quadratures or multiplying with quadrature signals, you can get back the amplitude and phase. Now, how we are going to use all this in terms of quantum uh, technology, let's say. So what we know, let me give you some examples where we can use all this. So for example, today what we understood is about the coherent light sources or Poissonian statistics, right? And we know that we cannot predict the photon arrival, so we have some sort of noise related to it, and this is called the short noise. And what we are trying to do is we are trying to measure things below the short noise limit. So we have detector in two regimes. One is the short noise limited system, one is the thermal noise limited system. What we would like to go is where the short noise is dominated, but we would like to go below that and try to measure there. But in quantum, what kind of signals are there where the signal is present, which is below the quantum limit, and we can measure it? So there are two aspects. One is the light source. So you have to create these kind of light sources, quantum light sources. What are these kind of light sources? So first is squeeze light. So squeeze light is a type of quantum light source. And in this light source, you can apply schemes or methods where you can try to detect the phase, for example. So what kind of technique? The technique is called homodyne detection, as we saw previously, that if we multiply with sine and cos, so if we have some signal, if we multiply by some quadratures, and then by doing that we can back calculate. So that can be done. So now let me briefly or very quickly try to explain you some techniques which we use in quantum. But I hope it is clear to you that why we have this short noise, because of some distribution, and depending on that we have some sort of light sources. So here we have a squeeze light source, for example, or single photon light sources, and these squeeze light sources, they also have their phase, and in kind of those detections we need some schemes to do the detection. and there we use homodyne detection or heterodyne detection. And now we will see what kind of technique is that and how we can create these squeeze lights, let's say. So let me first explain you the problem with this short noise. So what is the problem? So for example, this is what we know. This is the meaning of a anti-bunch system, or a light source, which is a single photon light source. It can be from any source, single photon or quantum dot. Now suppose there is this light source and light is coming from here, and there we have kept a beam splitter. This beam splitter is nothing but it will be some material, and there will be some coatings in front of this beam splitter, right? Now once the photon which is coming in this stream, they will hit this beam splitter and then they will split. Some of them will go to this transmission and some of them will go into reflection, right? Now since it is this beam splitter is a lossy media, so there will be the process of absorption. Now the process of absorption is a random process. So this is what the stream of photon which is coming, and after this lossy media, it is possible that some of these photons is getting absorbed inside this medium. And once those photons is getting absorbed, the your whole process of creating anti-bunched light source is getting reduced, meaning now there is more fluctuation because some of these photons are randomly going away from your stream of single photons. So your output one or two can become something like this. But what you have to respect is this law, is that your total fluctuations should not go more than the mean value of under root n. So if you are within below that limit, that your single photon source is fine. So if you have something like this, then you still are able to measure your single photon statistics even after the beam splitter, right? So your deviations should always be minimum of your under root n, and then you are always below the short noise limit, and then you can measure it. So keeping that in mind, let's now try to create a squeeze light. And first we create the squeeze light and then we try to measure this squeeze light. So let's say in electromagnetic theory or in classical physics, this is how we represent any electric field, right? So we have some sort of omega frequency phi, and that is the direction of propagation, and that is the amplitude. Now the same can also be represented in terms of a phasor. So phasor is nothing but a imaginary vector plane. So here we have y-axis, imaginary, and the real, and that is the amplitude. So this phasor or the vector represent the amplitude, and this represent the phase, meaning this angle. How much is this angle? That will show you the phase. So for example, if that is a wave, at this location there will be a different phase, at this location there will be a different phase, at this different. So this phase information is noted here, and the total amplitude which is fixed, and this amplitude is here. If amplitude goes up, then we can make a different circle with a bigger radius. So that is the information which can be represented either in terms of this or in terms of this. Now what we do is, why we do this, that is the point. So we do because the total magnetic field strength is quite low as compared to the electric field. You are seeing we are dividing with the magnitude of 3 into 10 to the power 8. So this value becomes quite small, and sometimes it is easier to deal in terms of phasor diagrams, right? So a same wave which is shown like this can also be represented here, right? And as I told you in the beginning itself, that the values which goes in x and y with the 90-degree of phase, they are called as a quadrature. So here x1 and x2 are quadrature components. So if you can find out x1 and x2, we'll say we can calculate the quadrature. And there are some rules which is comes from Heisenberg uncertainty, and which goes like this, that you cannot measure position and momentum with a specific precision. There will be always some sort of uncertainty. And in terms of phasor, this can also be written something like this, that in terms of phasor there is always the uncertainty. So one, suppose if you have calculated this phase, you cannot tell me the amplitude with perfect precision, or other way around is also true. So that is for the uh, quadratures. Now there are two different domains. One is the quantum picture and one is the classical picture. So that's how a wave you represent in classical physics, and the energy is given by this. So for example, if there is no wave or there is no intensity, what we typically say is that energy is given as zero, right? But in case of quantum harmonic oscillator, this is the energy which is given. And even if there is no photon, n is equals to zero, meaning energy is still there. And this is called zero point energy or fluctuations or vacuum field. So this is the vacuum state, meaning at zero there is uncertainty in this direction, which is half. There is uncertainty in this direction, which is again half, and because of that there is this vacuum state. So this this formula here, so what I was giving you here, the reason for this comes from the next slide, is that these two are the quadrature, and because this comes because of the uncertainty principle, or you can also say from this vacuum state that even there is no photon, there is always the uncertainty is there. So that is the vacuum state. Then comes the coherent state. So meaning, again, I will now use phasor diagrams to explain things, but in terms of quadrature, is that either you could say this is x1 quadrature, this is x2 quadrature, or you could say this is x-axis or y-axis. You could also plot similarly that on x I have position, on y I have momentum, or you could say I have amplitude on x or I have phase in y. This all is the same thing, is that what you are trying is you are trying to measure two different quadratures. So if you talk about in terms of electronics measurement, this is homodyne measurement. This is usually what you measure, amplitude and phase. Talk about quantum, what you measure is momentum and positions. So suppose electromagnetic wave is there, and this is the phasor for the amplitude. Now the problem is that there is always the uncertainty that you can also make one more like this. So you cannot measure very precisely, because amplitude you have measured precisely. Now phase is not properly measured. So phase can be anything. So because of that, you have this kind of uncertainty. So I have given you multiple different examples that why there is this uncertainty is there in terms of different quadratures. And I told you that if this is a wave, right, the red color is the mean value, and whatever you see with the black is the dotted. uh, these are the uncertainties. So this is the uncertainty in terms of amplitude, that you cannot measure the amplitude properly. It's here or up to here or up to there. So there is the uncertainty in the amplitude, right? But that is the mean of this wave. So this whole wave can also be represented something like this, that you take x-axis, you take y-axis, and you try to make a phasor like this, and this phasor has some sort of uncertainty. So what we have given here is the same thing here, and then this wave can be representing by this, and this way is more simpler as compared to doing it like this. So here I will show you this video, and then this video also shows you the same thing, is that there is this wave which is propagating, and this propagating wave can also be shown by changing this phasor, or this phase, this uncertainty is there but is rotating around this circle. So that is about amplitude and phase of a wave, that amplitude is also not certain and phase is also not certain. So there will always be some uncertainty, that this is the amplitude noise, that you cannot calculate amplitude precisely. And similarly in terms of phase also, you don't know where is the particle is at this location, whether it's here, here, or here. So in both the cases you have uncertainty. Now what you could do is you can squeeze or make the uncertainty lower in one direction. What do I mean by that? So meaning this is amplitude squeezing. So in this case, I have amplitude here and phase here. And what I have done is that I have reduced uncertainty in phase, meaning some sort of balloon you can understand. You can reduce the uncertainty in one direction. Suddenly the uncertainty in the second direction will increase. Now, similarly, you can consider this again as a wave. And then if this wave is propagating, That's how it looks like. So you can very precisely tell me that this amplitude is this much, but now the phase you cannot tell. So the uncertainty in phase has increased. So this is called the amplitude squeeze light. So I'm just explaining you what is the meaning of creating squeeze light. We can create two type of squeeze light, either amplitude squeezing or phase squeezing, and this time we have done the amplitude squeezing, right? And doing amplitude squeezing meaning, in one of the quadrature, meaning in amplitude quadrature, in this quadrature we have reduced the noise, we have gone below the short noise limit, but the impact of this is that in the phase, now we cannot tell the phase, the uncertainty has increased. So there is a limit to that, but we can go below that limit only in one quadrature. So the phase noise and increase, and you can do different type of squeezing. So that is the coherent state, where n bar meaning average number of photons is not zero. It looks something like this. In case of amplitude squeezing, at this you have increase in terms of phase, the noise has increased, and in terms of amplitude it has decreased. And then similarly you can create the phase squeezing, meaning here the amplitude you cannot tell because uncertainty has increased too much. It can be here or it can be here, but the phase you can tell very precisely that the particle's location is very precisely defined. So that is about the generation of squeeze lights, that you can generate squeeze light with different types. But suppose I have this kind of light, but then how do I measure this? So what you have to do is to do homodyne detection in order to measure the quadrature, meaning when I said I squeezed in amplitude, so what do you want to know is the amplitude quadrature. uh, when I squeezed in the phase, what we want to know is the how much is the reduction in the phase quadrature. How do you do that? So what we have is a beam splitter here, okay, and this is our signal here, which is given as psi. So this is our signal which is hitting to this beam splitter. And I told you in the beginning is that in order to do homodyne, we need a local oscillator. And what you have is a local oscillator where the strength of the local oscillator is quite high, given as a beta, and its frequency is same as the input. So this you can consider that suppose either we have a laser or we have an oscillator with the same frequency to signal, but the intensity of this is quite high. In terms of signal, what do we have? So we can have a phase squeeze light or amplitude squeeze light, and which has very low number of photons, right? That is what we have at the signal. What happens once this one and this one, these two interfere at this beam splitter, you get a tensor product of state psi1 and beta. Now this tensor will, so this D3 and D4 are detectors. So this light will go here, it will get reflected, transmitted. Same will happen to A2, got reflected and transmitted. And finally you have two outputs, A3 and A4, which is going to your detector. So finally what you could do is, depending on these incident photon, you can calculate the current on these detectors. So on detector D3 and D4, you can calculate the current. Suppose if you know the current, meaning you also know the intensity of incident light, meaning the photon relations. What is the relation of that photon? And if you know that, then you can trace back what was your light source, whether it was amplitude squeeze or phase squeeze. So this is what we are going to do. So the formula finally is I3 I4, meaning I3 minus I4. So you take the difference of these two current on the detector, and finally this is how it looks like. Psi was your actual signal, and what you have applied is you are measuring a quadrature of your actual signal, which is given, quadrature is given by x, psi is the phase, and beta is the amplitude of your local oscillator. So you have increased. So suppose you have given this current value, you divide it with the beta. So what you have is current value, you divide with the beta. So what you get is the quadrature of your signal in terms of phase. Now you can keep changing this phase, keep calculating this current value, and what you can construct is a phase distribution. So you get the complete phase distribution of your let's say amplitude squeeze light or the phase squeeze light. So that is the basic mechanism with which you can measure the quadrature of your signal. So in electronics, it is not that easy to do, but in optics, it is very easy. For example, to generate a light source which has the same frequency or wavelength of your incident signal. So now what we can do is, by multiplying this beta, what we are doing is we can boost our signal. So that is the one thing. And second, by changing this phase and keep measuring this current, we can calculate the phase distribution diagram. So that is a very famous paper regarding this phase distribution calculation. This was published in 1997. And if you look at this paper, what they have done is, so just let's try to discuss this. So on the first panel figure, in the y-axis, we have noise current, right? So I told you we have to measure this I3 minus I4. This is what they are trying to measure in the y-axis. And what you see is the very first is the coherent state. So if this would have been at the center, this is called the vacuum state, which will be this one. But this is the coherent state, and that is the amplitude quadrature, and that is the phase quadrature. So for example, in this quadrature, this is quite too much. This is the amplitude extension, meaning noise is too much in the amplitude. This is the phase quadrature, meaning the noise is less in terms of the phase quadrature. So if you try to trace this here, meaning noise in the phase is lower, meaning you can calculate the phase very precisely, but amplitude you cannot calculate. So the noise in the amplitude is quite high. Similarly, you can also see that this is amplitude squeeze light, meaning amplitude you can measure very precisely, but the phase you cannot tell at which location the particle is. So different kind of squeeze lights are being created, um, and depending on that, you can calculate the signals. So now let's see what is given here. So what you can see is this is a kind of a wave distribution, right? This is also a wave. So this is called the phase distribution diagrams. So on this axis, what you have is the phase from 0 to 2 pi, and what you have from here to here is the amplitude, which is given from minus 10 to plus 10, right? And here is the distribution by changing the phase value. So what they are doing is, for example, in the previous slide, if you see this beta, so that is the amplitude which you have to increase of your actual signal. So they have considered that as maximum value of 10, let's say. So this is the oscillator maximum strength, which they keep at 10. So that is the plus 10 and that is the minus 10. Now you start changing your phase. So first it was 0, then you change it to 1, 2, 3 and up to pi. And then you again go from pi to 2 pi. Once you do that, for each particular phase value, you will get a current value. And this current value you can try to convert into probability distribution. And then this distribution you can try to calculate for all theta. So what you have finally created is a phase distribution, or we can also call it in terms of quantum is a Wigner distribution. So for example, this is amplitude squeeze light. So here you see that the amplitude is getting squeezed at certain locations. So not all the locations, but at certain locations. So for example, here the amplitude is not squeezed, but at this particular location you can calculate and you see the amplitude is getting squeezed. And the similar you can also see in this diagram, that at certain locations this is the amplitude and this is the phase. So phase is getting, and the amplitude is getting reduced, and this is happening at different phases. So how do they do all this? So for example, that is the complete setup. This is how it looks like. So if you see from this to this part, this is just to create a squeeze light. So what they have used is an ND-arc laser together with the uh, filter cavity. So they filter the laser and use a optical parametric amplifier and electro-optic modulator, and together with this combination, what they create is a signal. Now the signal can be amplitude squeezed or a phase squeeze light. What they want is a local oscillator. So this laser is coming from here, and then through this beam splitter, half of the laser is going here and the remaining laser is coming here. So they have created a local oscillator with the same frequency of light. What is the frequency or wavelength of this laser? The same wavelength is present here. Now signal is coming from here, and this is the local oscillator coming, right? That is the local oscillator. Now here we have the same beam splitter, which I was telling you. The interference will happen here. From here the signal is coming, and from here your local oscillator is coming. After this we have two detectors. So in these two, at the beam splitter, interference will happen. So you have A plus B and A minus B, right? And the A plus B is the high frequency signal, and this high frequency will be removed using a low pass filter. So only the low frequency A minus B signal will be there. So I3 minus I4 current will be there, because here they subtract these two current values. Once you do that, finally, by changing this phase of the local oscillator, you can create that phase distribution diagram. So you keep changing your phase from this location, and you keep calculating this current value. And what you will see is that here is this current value. So you keep changing that, and for different phase, you can try to plot this Wigner distribution function. And similarly, by doing this diagram, they try to plot this. So this is the way of characterizing a quantum light sources. So we have created a quantum light source, meaning a squeeze light, by using this particular setup. And then finally, in order to characterize that, the homodyne detection is required. So I hope clarity you got with these lectures. And with this, I would like to stop. And in case if you have any questions, please feel free to ask.
Thank you, sir. Can you just see the chats? There are few questions in the chat box. You can stop sharing and then I think better.
Mm, okay. Yeah, I think now, yes.
Yes, perfect.
So due to the uncertainty, the actual photons counting may be deviated. Yes, so this is due to the uncertainty in the source itself. So in the laser source, you have the uncertainty, and because of that, uncertainty is carry forward towards your detector, and because of that, you have deviation in the counting. So in case of Poissonian light source, that is the case, but in quantum light sources, that is not the case. So there you have equidistant photons, and the distance is equal. Why is it called homodyne? So homodyne is direction. For example, in the last slide, what I showed you is that when we have the laser, we use the same laser to create the local oscillator. So when the frequencies are same or the wavelengths are same, we call it as a homodyne direction, and if it is different, then we call it as a heterodyne direction. So typically, what we do is a heterodyne direction, because in general, even if you do a beam splitter and use a laser, it is very difficult to create same frequency or wavelength. Is it it is necessary that the quadrature, yes, quadrature are orthogonal to each other. So what I mean is that, so how can we prove that? So amplitude and phase, this you can calculate just by, for example, what I showed you is that if you have an oscillator, you put signal together with sine or sine omega t, and the second time you put it with the cos omega t. So this sine and cos omega t, they are quadrature to each other, meaning you have 90 degree of the phase difference, and by doing that you can calculate the amplitude or phase. And in the second diagram, when I showed you by two axes by putting uncertainties, so in terms of uncertainty, I mean is that if you have a Heisenberg uncertainty in the position, so you can calculate one. So what you see here is that if you can calculate amplitude precisely, you cannot calculate phase. So in that sense, they are orthogonal to each other, meaning you require some sort of homodyne direction or some 90-degree phase quadratures to do that measurement.
Any other queries? So if there is no other query, let us thank the speaker again for his talk. So thank you, Dr. Vaibhav, for your time and
Thank
talk
you,
today.
sir.
It was wonderful to have you for like in various sessions.
Yeah, thank you, sir. Thanks a
And I
lot.
hope uh, fabrication, how, what?
Mm, no, sorry. I mean, I think I did not get it. Fabrication, or you mean how to fabricate the detector, or uh,
Okay, so this is, I think